our project is titled Evil and the Quantum Multiverse. It's an exploration of a couple of things. Number one, of how thinking about value and thinking about especially kind of reckoning value and value aggregation can take different forms depending on how things turn out in terms of fundamental physics, which is surprising because a lot of axiology kind of gets conducted as if concerns about what the world is like at a fundamental physical level are irrelevant to the project of figuring out what's valuable or what our obligations are or how value combines to sort of create these assessments about the goodness or badness of a world or a history. But also it's exploring a version of the argument from evil against theism that has been noted in a couple of places as maybe particularly difficult or particularly vexing. And so one of the things that we end up learning by kind of attending to fundamental physics in thinking about the argument from evil is that the interaction between the theory of value and the physics shows that this argument doesn't necessarily go through, so that it's not a solution to the ordinary problem of evil, but it does. But we are going to argue that if you shift to a particular interpretation of quantum mechanics, the problem doesn't necessarily get worse. So plan for the talk. First, we'll say a little bit about the Everettian theory of quantum mechanics, what motivates it, why we would think that there are these mini worlds or this multiverse. Then we'll talk about how that might kind of intensify the traditional problem of evil. Then we'll talk about why this suggested intensification is a mistake, kind of with paying attention to the details of what it takes to make an empirically adequate version of Everettian quantum mechanics. And this will kind of bring out the major lessons about value aggregation and fundamental physics. And then we'll think about some objections. All right, so step one, the physics setup. And this begins with the measurement problem. The measurement problem, we can sort of think about if we look at three inconsistent premises. Premise one, which says that the wave function is the complete description of a physical system. Wave function is a mathematical device used in quantum mechanics. It's one of the major objects of study. Number two, the dynamics of the wave function evolve according to the Schrodinger equation. So if we say that that's the complete dynamics, in other words, the wave function just evolves forward according to the Schrodinger equation. And then premise three, we have unique outcomes of experiments. So when you say observe a cat, what you observe is either a live cat or a dead cat. Or if you observe an experiment, you observe pointers going in this direction or that direction. So these are all three fairly normal, and at least in the case of number three, common sense things to say. Given the way that physics is generally coded, the wave function is meant to be a complete description of a physical system. The dynamics are supposed to be given by the Schrodinger equation. And when you look in the world around you, you don't see more than one outcome for a given situation or a given experiment. The problem is those are inconsistent, and this is what Schrodinger's famous cat thought experiment brings out. So just to remind everybody of Schrodinger's cat, you have this setup where there's a cat in a box alongside this device that has some radioactive decay and a measurer and some poison. And so if this atom in the measurement device decays, then the poison's released and the cat dies. If it doesn't decay, then nothing happens, the cat's alive. So for the experiment, you wait one half-life of the atom, so it's 50-50 whether or not the thing decayed, and then you open the box. And then intuitively what happens is you look inside and you either see a live cat or a dead cat. That's what's supposed to happen. The problem is that's not what P1 and P2 tells you is going to happen. So starting out with the wave function of the system, there are sort of two ways broadly speaking, that it could evolve. It could evolve forward to a dead cat wave function, or it could evolve forward to a live cat wave function. And the Schrodinger equation tells us it's going to move deterministically from this initial setup in that direction. But it tells us it's not going to quite go to either the fully dead cat version or the fully live cat version. Instead, it's going to go to some kind of mixture of it. And there's a mathematical formula that gives us that. The details of the formula are going to be super important. But what you end up getting is this thing that Schrodinger describes as a situation where the cat is smeared out between dead and alive. That is a superposition. And the point of the thought experiment is that while the mathematical theory of quantum mechanics predicts that there are superpositions everywhere, you don't, in fact, actually go around seeing superpositions, especially in macro objects. And this is the measurement problem. It looks like you can't have P1, P2, and P3. So then a significant part of the game in giving the foundations of quantum mechanics has been to decide which of these to give up, at least if we want to stay realists about the theory. So one theory, known as Bohmian mechanics, gives up P1 that says, look, in addition to the wave function, there are particles in physical space with precise positions. And so we supplement the theory to account for those. You give the guidance equation that tells how they evolve. And then when you do that, you can recover unique outcomes. So that's one approach. Another approach, the GRW theory, which is just the initials of the physicist who wrote it down, says actually, like P1 is fine. The wave function describes everything. P3 is fine. It's P2 that's the problem. You don't always get deterministic evolution. According to the Schrodinger equation, we have these things called collapses. So given more particles in the system over time, the system kind of resolves into these non-superposition states. It jumps. That's the spontaneous collapse. And that's why you don't ever see the cats in superpositions. The third one is the one of interest to us today, the Everett or many worlds interpretation of quantum mechanics. And the Everett interpretation says P1 and P2 are fine. That's just like the textbook theory of quantum mechanics. The thing to give up is the unique outcomes. Instead, you, the observer yourself, are not independent of this cat poison radiation detection system. When you interact with it, you get caught up in its evolution. And if you were able to like take a view from nowhere of the entire universe, what you would see are these multiple branches, one branch with a live cat, one branch with a dead cat, one branch with you observing a live cat, one branch with you observing a dead cat. So the reason that you don't perceive yourself as observing a superposed cat is because you yourself are part of these superposed objects. If you could sort of like stand outside the wave function of the universe and look down on it, you would see the branching structure. So that's the idea behind the many worlds interpretation in a nutshell. And what that means is that any forward evolution of the wave function that the laws permit happens somewhere. Any way things could have gone, there's a branch like that. And some people have thought that this poses a problem because it looks like you're going to end up getting all sorts of terrible possibilities fully realized. So this worry has been put forward kind of most notably by Dean Zimmerman in a Nautilus article, by Jason Turner in a manuscript, where they argue, look, so you've got these what they sometimes call evil verses, branches full of endless suffering and nothing that could remotely justify the suffering. As far as we can tell, the laws allow for histories like that. They're super unlikely. So if you only have one world, like in a single world quantum theory, they're not at all what you would expect, but they're not illegal. The laws of nature don't rule them out, which means in the Everettian version, where anything the laws permit shows up on some branch or other, given the starting conditions of the system, you will end up with some of these really bad branches. And then there are sort of two ways of precisifying really bad. So one way of specifying really bad, you could think of it just has large quantities of evil. Think just lots and lots and lots of people doing lots and lots and lots of suffering. But it could be fairly anodyne suffering. It could be a branch full of people stubbing their toe every minute, something like that. Or you could think of it in terms of qualitative suffering. In other words, think of the most sort of horrendous, soul-destroying, meaning-canceling sorts of suffering. I'll spare actually giving examples here, but you can find them if you go read the literature on evil. And there you've got a different sort of problem, because it's not just sort of the sheer quantity of toe stubbings going on. It's this sort of maybe deeper or more concerning sort of thing. And you can give versions of the problem with both of these in the Everettian setting. So that's the concern. The concern is that in a single world, you've got these horrific histories that have low probability, but that's it. As long as they don't happen, they're just kind of there as looming non-actual threats. Whereas in the Everettian version, you've got these horrific histories. And they do have something called a low branch weight, which we'll get to. But there's at least some sense in which they're real. And so if you thought it was concerning enough, the evils that we've actually observed, well, all the evils that you could have potentially observed, this theory tells you, are out there somewhere. Okay, so now we need to do a little diversion through how different sorts of operators can modulate the correct response to a sentence. What we call in the paper, the metaphysics of diminishing value. So first, kind of a beginning example. Take the sentence, there's a massacre where 100 people die. Depending on what you attach to that sentence, the proper response and the proper kind of accounting for it in terms of ethics will change. So if you just learn the sentence, that's something bad, there's an appropriate reaction, there's going to be some mixture of sorrow, indignation, moving to prevent it, etc. Now let's say you learn in the past, there's a massacre where 100 people die. Well, now the reaction is different. It's already done. It could be a moment for memorialization, still an occasion for sorrow, but crucially, there's not anything you can do about it. So there isn't really a call to action, at least to preventative action. There might be a call to memorial action. There might be a call to retribution. But the morally functioning response is different. Now let's try a different operator, say a possibility operator. Say possibly there's a massacre where 100 people die. Once again, the reaction changes. Here, concern, maybe avoidance, but mere possibilities are not necessarily that scary. So it's a much, much more recessed reaction. Well, it turns out some of these relevant operators have probability in them. And that's going to be important because, as we'll see, the concept of probability is sort of fundamental and crucial in making sense of the Everettian picture. So if you learn with a probability of 10%, there's a massacre where 100 people die, you still ought to do something. Like, that's still bad, and it's still a bad expectation. But it's less crucial than, say, you learned it at probability 50% or at probability of 75%, and definitely different than if you learned it at certainty. So probability operators sort of, by their nature, modulate the correct response to whatever falls under their scope, whether that be a sentence or a declaration or something like that. Anything that doesn't do that isn't a probability operator. That's just part of its job description. Now let's jump back over to the Everettian interpretation of quantum mechanics. So the way the Everettian interpretation works, you have this thing that physicists call decoherence. And it's what guarantees that the various branches of the wave function don't interfere with each other. Because what you have fundamentally is just a wave function. The branches are what's known as emergent. And crucial part of this emergence is that the various branches don't really interact. That's why we get to consider them separate. But when you look at the mathematics, they're not completely separate. What you have is this low branch weight to the branches, and low weight to them interfering to the branches interfering with each other. And so in order to understand the emergence at all, you need to be able to argue that the branches don't interfere. And the typical way of doing that is to say that it's very unlikely that the branches will interact or interfere with each other. That's crucial to making decoherence work. What that means is that the concept of probability has a really important role in making sense of the emergence of macroscopic objects, which can be things like people and buildings, cats, the things that we actually think of as value bearers and is mostly relevant to ethics. Because when we're thinking about ethics, we're not thinking about fields and functions and particles for the most part. We're thinking about the bigger objects that are made out of those things. To make sense of that, you need to have a concept of probability in place. You can't have decoherence without probability. And so typically, Everettians want to count the branch weight that the wave function assigns as probability. And you do that according to something called the Born rule. It's the Born rule statistics that you use to match the observations that confirm quantum theory in the first place. So it's really important in making sense of the Everettian picture that you get a particular probability distribution. And probability operators, as we pointed out, have a number of jobs. Yes, they encode uncertainty, but they also interact with ethics and rational decision-making in an important way. And it's that interaction, together with their sort of crucial role within the Everettian picture, that we're going to leverage to then argue that this Everettian problem of evil isn't actually any worse than the ordinary problem of evil. All right, so comparison time. In a single world, we have one actual history, lots of possible histories, and we take expected value by sort of looking at the probability weighted outcomes. In an Everettian world, we have a bunch of branches, but branch weights play the role of probability, and Everettian quantum mechanics doesn't work if branch weights don't play the role of probability. As a result, when we do our moral evaluation with our expected utility calculation, we need to use branch weighted outcomes. In both cases, you get a formula that looks the same way, an expectation of values by the weights. I mostly covered this slide already. All right, so how do Everettians justify this? After all, if you just look at a picture of a branching multiverse, what you end up with is just a bunch of branches. In a sense, they're all real. And you can't get branch weights by just counting them. That's not going to work. That's going to come out with a bunch of symmetries that you just don't observe. You don't recover the Born rule predictions, and so you don't even get an empirically confirmed theory. Instead, what you have to do is you use this piece of mathematics, the psi squared. That gives you branch weights. And that allows you to then have probability. But why should that matter? This is just a piece of physical stuff. We don't go around like counting particles and using that to make rational decisions. So how would branch weight, which is just a thing that you pull out of a wave function, why should that correspond to probability? That's sort of a key pressing question for Everettians to answer. And the most promising strategy that Everettians have come up with is known as the decision theoretic strategy or the Deutsch-Wallace strategy. And there, they take inspiration from Savage, von Neumann, and Morgenstern, sort of the classic decision theoretic tradition, where decision theorists were interested in recovering probability and value from the preferences of an agent. So the idea behind early decision theory, going all the way back to Ramsey, is that if you look at an agent's binary choices, I prefer this to that, you can use those to sort of systematically extract their beliefs and desires about the world. In particular, there's another piece of math that relates an agent's preference relation, which is just a relationship over acts. Think of things like going outside or staying home, or taking my umbrella when I go for a walk versus leaving my umbrella at home. Choices over that to a probability function and a utility function that encodes their beliefs and values. A piece of math called a representation theorem. And so it's been proven, in fact, there are several of them out there, if preferences satisfy certain sort of coherence and richness constraints, then there exist these two functions, a probability function, a utility function, that represent the agent as an expected value maximizer. And so Deutsch and Wallace thought, well, if we can show that rational preferences ought to maximize expected utility when you think of the probabilities as given by the Born rule, that would show that branch weights are the kinds of things that should guide our decisions, i.e. our probabilities. So that's sort of the core of the Deutsch-Wallace strategy. You count branch weight as probability, and remember, you need it to be probability in order for decoherence to work, in order to get branching structure at all in Everett. You count branch weight as probability because it answers to one of the key roles of probability, namely serving to guide rational decision. And so the representation theorems that they proved are sort of the mathematical proof of work to show that, yes, you can set down some axioms of rationality. And once you do that, there is a way of thinking about branch weights as giving the correct probabilities to guide action, including moral evaluation. So we have on this slide here, we have a diagram that shows exactly what's going on with the emergence of probability and value in an Everettian world. And because we're dealing with the problem of evil, we've stuck God in there. So we're thinking of God's preferences as sort of the paradigmatic rational preferences in this picture. So you'll have divine preferences. They need to correspond to the Deutsch-Wallace axioms. Then you have a wave function. Our representation theorem takes us from divine preferences to probability and utility. We need that probability in place along with the wave function to get branching structure. And the branches are the things to which the probabilities and utilities attach themselves in the first place. Now, quick note, some of you will see that there's a little circle there through the line that we've labeled precondition. That's been the basis of an argument in the literature that Everettian quantum mechanics doesn't make sense because its use of probability is circular. We're not taking a stand on that. So we think this is the correct diagram. Like if you're doing a graph of how probability and utility work in this situation, the graph we've given is the right one. Does that kind of circularity also refute Everett's theory of quantum mechanics? And if it does, a lot of our job got a lot easier. There's not an Everettian problem of evil if Everettian quantum mechanics doesn't work. So like dialectically, it wouldn't make sense to go that way. Instead, we're going to assume that it's not a refutation, that the circle is a virtuous circle, which is what Everettians have contended. But its presence is important because it tells us the order in which to think about probability and value. Namely, in this picture, the values that attach to things, like the branches, macroscopic objects, are downstream of the expected value. So when you're evaluating whether to create a world a certain way, you don't think, what's the actual value of this thing? And then the expected value just encodes your best attempt to get at that through the haze of uncertainty. Instead, you have to ask, what's the expectation value? And once you have the expectation value, then the actual values all resolve. So the order is flipped from what you would get in sort of a standard classical physics only model. So you have God sitting there trying to decide what world to create, thinking about which wave function to choose, thinking about how to build its fundamental structure. In the single world case, you'll have a wave function, you'll have the sort of starting probabilities that you need to recover quantum mechanics. And that's it. You can then sort of look and see, okay, how's this starter wave function going to evolve? And that's going to give you the value that you can attach to a single world. In the Everett case, in order to get the actual values on the branches, you already need the probability, and therefore you already need the expected value in place. So that's what you think of first. And this has to be how it works if branch weight plays the role of probability. And branch weight has to play the role of probability in order for Everett to be an empirically adequate theory at all. Okay, so that brings us to the end of our sort of primary line of argumentation, which I'll sort of recap before I talk about the four main objections that we've considered. So the problem is coming out of the Everettian theory of quantum mechanics. The theory says we don't live in a single world. We live in this multiverse with lots of branches, splits that happen every time some other theory would say that the wave function has collapsed. Every time there's an observation event, there's sort of different ways to put what exactly the Everettian slogan should be here. Given that there's a concern that the universe is way, 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 way worse than you would have thought. Why? Because you've got all of these branches full of horrendous suffering that are in some sense real. That makes the problem of evil, like however bad you thought it was, it's significantly worse, both in terms of quantity of evil and in terms of quality of evil. Our solution is to say, wait, if an Everettian multiverse was just a weirdly shaped classical universe, that would be right. In other words, say Newtonian physics or something near enough is the right one, and you just have a space-time with a funny shape, that would be the end of the story. But that isn't how we got there. We got there through this emergence of branches from a wave function through a process of decoherence. And in order for decoherence to work, you need to have the concept of probability, because what tells you that different branches don't interfere with each other, because they overlap a little bit in configuration space. They're not totally distinct. But what tells you that you can ignore any interference is that it's such low probability. But where would you find probability in Everett? If you look at the theory, you just have a wave function and you have a deterministic equation that guides the evolution of the wave function. Nothing that looks chancy or stochastic or anything like that. So to find it, what you have to do is you have to find the piece of the theory that answers to probability's typical functional role. It's typical one of its typical functional roles. So one is to encode uncertainty. Another one is to guide rational decision and to guide sort of appropriate moral reaction. That's what the discussion of operators and diminishing value goes to show. And if you follow the Deutsch-Wallace strategy, you've got just some axioms that tell you if you're a rational agent, you maximize expected utility according to the Born rule weights, according to the branch weights. Then you can treat this thing that is in the math, the branch weights, you can treat that as probability. If you're entitled to treat that as probability, then decoherence makes sense. So the emergence of macroscopic objects in Everett makes sense. But probability and expected value is sort of more fundamental. than actual value. So when you're deciding which world to create, say, because everything I've said about rationality applies to a creator God as much as anybody else. When you're deciding which world to create, you have to reckon value via expected value rather than via sort of like counting up the actual goods and bads on the kind of final thing that you get. And when you do that, you're going to find the expected value of a given wave function and starting probability is the same whether you do a many worlds quantum mechanical creation or a single world quantum mechanical creation. So given the same wave function, a single world, a many world, it's going to be the same expected value. Now, the expected value of the one and the actual value of the other may not match up. They probably won't. So once you sort of run that single world forward, let it all happen, the actual value you get is not going to match up to the expected value of your multiverse. But it could go either way in the decision. It could be better, it could be worse. So whether or not it's better or worse, kind of from the standpoint of actual value, to go with a single universe or the multiple universes, there it's less clear. But the point is, when you're making the moral assessment of the choice of wave function, if your quantum mechanics are Everettian, expected value has to be first. Okay, so another worry that's been brought up to us here. Look, thinking maybe we've answered the quantitative problem. What we've effectively done is given a way of discounting bad things on low branch weights according to the weight of the branch. So back to our branch with everybody stubbing their toe. All right, we discount that by the branch weight, and maybe that comes out in expectation to not being measurably worse than a snowstorm in the middle of the winter or something like that. But there are some things, this version of the objection goes, that simply shouldn't be allowed. So again, think of your kind of deepest, darkest wrongs. They are absolutely prohibited according to a deontic theory, or disallowing them is a side constraint, as a decision theorist would put it. And we haven't solved that problem because we've granted that the bad branches are in some sense real. So even though we've found a way to attach formidable discounts to the evils on these branches, they're not banished from reality the way they would be if a single universe was true and they didn't happen. So how do we respond to an objection that says, look, the core of the Everettian problem wasn't quantity, it was quality? Well, here's our response. First, we remind everyone that we're not offering a theodicy. So the goal is not to say that there's no problem of evil. The goal is just to say that it doesn't get worse if you shift to an Everettian quantum mechanics. And then we'll say, look, for every branch that you have in an Everettian world, you have some possibility of that occurring in a single world. Why? Because if the possibility wasn't there in the single world, that just means that wave function doesn't go there. And so then there won't be a branch like that in the Everettian world either. So low branch weight in an Everettian world corresponds low probability in a single world. So then we can ask ourselves, how do standard theories of uncertainty handle absolute prohibitions or handle side constraints? And it turns out like it's really hard to do better than the rule that says allowing some probability of violating a side constraint is as bad as violating a side constraint. In other words, if there are absolute prohibitions, it's also absolutely prohibited to risk them. In which case, that's going to be a strike against the single universe version of this wave function with evil branches, just as much as it is a strike against the Everettian version. Now, maybe there's a better way of dealing with risk in absolute prohibitions, but if so, deontologists haven't found it yet. That's the latest, greatest in that literature is still at risking violating a side constraint is just as bad as violating a side constraint. So that restores parity. All right, so final objection before I close. And this one is based on a different discussion of ethics in multiverses. So some people may know, some may not, kind of depends on your background in metaphysics. David Lewis had this proposal that all the possibilities, not just the ones that the laws of nature allow, but the ones that kind of logic itself allows, are out there somewhere. The much, much bigger multiverse than Everett's, and his worlds were absolutely separated. Why did he think that? It would take a while to explain, but he thought that that was in some sense the simplest theory of reality, and that he could do a lot of really interesting philosophical work with it, which the second of which was undoubtedly true. This is his book on the plurality of worlds. One of the famous early objections to Lewis came from Robert Adams, who said, look, Lewis, it's at least somewhat important to ethics that we be able to alter the balance of good and evil in reality, and your theory doesn't allow that to happen. Any bad thing that I prevent here just happens in one of your other possible worlds. So what's the point? Lewis kind of gave a response to Adams that basically said, look, only care about things you can causally affect. So shouldn't bother me if bad stuff happens outside of my area of effect, as long as I've kept my area of effect as good as I can. We basically think Lewis had the right response in that exchange. So you could level a similar objection to us. Look, in some sense, the amount of good and bad things is settled by the nature of the wave function itself. The branch weights tell you what's more and less likely in a way that should inform your rational decision making. But the low probability branches are there, and there's not anything you can do about that. Our response, kind of inspired by Alistair Wilson, who's given a modal theory along Lewis's lines that uses Everettian quantum mechanics as its background multiverse, is to say, yeah, what you should care about is not the whole wave function, it's just the actual branch, because that's the only thing that you can affect. And as long as you have the care about stuff you can affect rule in place, then you can recover basically all of common sense ethics. All right, I think that brings me right up to the 40-minute mark. So with that, I'll go ahead and stop and move to Q&A.
Thank you so much, Daniel. You are right on time.